We use Newton's second law to find the net force and the final and initial velocities, as we can see using these equations right here. For my experiment, I recorded a paper ball of mass 0.007 kilograms being dropped. Here's the video and the tracking of the paper ball. I then used VPython to create a computer model of the ball's motion if gravity were the only force acting upon the ball. Here we can see that I added in the ball's mass of 0.007 kilograms, the initial position, which is 0, 0, 0, and the initial velocity being 0 because the ball was dropped from rest. I made my time step 0.001 seconds to make sure I had plenty of data points, and the acceleration due to gravity 9.8 meters per second squared. J hat equals the vector 0, 1, 0 to show that we're looking for motion in the y direction. I used 0.668 as the time because it's my final experimental time. Because we're only looking at the force of gravity right now, we made F net equal to W, which is the ball's weight, which we found by multiplying the ball's mass times the acceleration due to gravity times J hat in the negative direction. We also added in the equations for the ball's final velocity and position. When we run the module, this is what it looks like. But we have to add in a drag force to account for why the ball doesn't fall as far as we think it should from this model. To do that, we had to change, we added in F net equals W being weight plus the drag force, where the drag force equals negative b times the ball's velocity. To find the drag constant, which is b, we had to look at the final y position of the experimental graph, which was negative 2.15, as you can see right here, and we had to make sure that that was the final position that the model showed. So we found this by running the model. And after it shows you this, you can look here, and this shows you the final position. And we see that the final y position is negative 2.150, which is the same as it is in our experiment. So then we added in arrows to show the force of gravity and the drag force. To do this, we used the arrow's position as the ball's position, and we used W times an arrow scale to show that it would be going in the direction of the force of gravity, and the arrow scale makes it into meters instead of newtons because the axis has to be a form of distance. To find the arrow scale, I knew that I wanted my gravity arrow to be 2 meters, so I did 2 divided by the weight of the ball. And then to find the other arrow for the drag force, we just did the drag force times the arrow scale, which shows when you do this. Here's the gravity force. For some reason, my drag force arrow didn't show up, and I tried to change the arrow scale to think that maybe it would be bigger, but it didn't work. I think I can attribute this to having a very small constant b, as it is only 0.000575. I then graphed all 3 of these sets of data on this graph, which shows the model data, experimental data, and the adjusted model data for when the drag force is added. The 3 curves are really similar, but it shows that in my experiment the paper ball fell faster than expected during this part of the experiment. It shows that the adjusted model position and experimental position are exactly the same at the very end, which is because that's the point we used to find the b constant. The reason that the ball fell faster during this part may have been because the ball was not a perfect sphere and parts were more or less dynamic than others, so technically the b constant would not have been the same for the entire time. There's also some movement in the x direction, as you can see in our experiment, and probably some movement in the z direction as well. So our perspective could have been slightly skewed because of this. There was also somewhat of a glare on the screen because I tried to do my experiment in bright light, but it kind of backfired because it was too direct. So it was hard to see the ball at points, which could have changed my tracking of it. I used the height of my friend as a scale, but it was kind of hard to decide where to put the bottom of the scale on the floor, which also could have changed my data. It's possible that there was a draft in the hallway due to a vent or something that was actually causing air to be forced down, adding an extra downward force on the ball and causing it to go more faster than expected. But overall, I think the model predicted the experiment well. If the ball had been dropped from a height that could allow it to reach terminal velocity, the model with the drag force would probably predict the terminal velocity much better because it would change the net force, which obviously would change the final velocity. If the ball had initially been thrown downward, it would also reach a different terminal velocity because it would start at a different initial velocity, which we can see using just these equations right here. That's it.